So I'm going to go ahead and just dive right in. So basically this talk is going to be how our piece of Texas evolved, the land mass, how we got it. So one of the resources I used was this book here, Texas Through Time, and it's a great one for all of Texas. So if you're interested in reading more about geology in Texas, this is a good one. Another good source is Roadside Geology of Texas. But this one, Texas Through Time, has some beautiful pictures. It's a lot more fun to look at. Okay, so my talk is going to focus mainly on two time periods, the Proterozoic down here on the geologic time scale. So roughly 1.6, 1.7 billion years ago is when Texas kind of got started. And then the big era for landmass being created here in North Texas was more in the Mesozoic, which is, the time of the dinosaurs. Okay, so I'm going to give you just a quick overview so you have kind of an idea of what I'm talking about with the geology tonight, and then I'll dip more into Texas. But in its very early days, Earth was kind of this, it was called the Hadean, and that meant hellish. And Earth was this big hot mass of lava. Um, the whole surface was molten, and that was about 4 to 4.6 billion years ago. It took a long time for the crust to solidify, for the oceans to get started, and we still didn't have a lot of land mass in the beginning. Once the oceans spread out, as you can see here, Earth was the land masses were really small. It was mostly large islands or island chains. And if you want to look at the timeline over on the right side, you can see here it was very early on. Plate tectonics got its start about 2.5 billion years ago or so. Okay. So this looks really busy. Don't be scared of it. This just kind of shows it's called the Wilson cycle, and it's how plate tectonics work. You'll have a basin, an ocean basin or a continent that will rift apart. And more ocean is being created. Then over time, it becomes more of a passive where the edges of the continents are very quiet and there's not plate tectonics going on. That's what's happening on our East Coast right now. As this continues, one of the plates will start to subduct and go under. One of the ocean plates will start to go under the continental plate, and that's where we get volcanoes. And with volcanoes and mountain building, we get more land mass. So this just kind of shows you that this is a cyclical thing. This supercontinent cycle happens over and over again, where ocean basins will open and then they close, which is over here in steps 5 and 6. They close back up again, and then it'll be stable for a little while, and all those mountains erode, and then it starts again. Someplace the basin will start to open, and it happens over and over again. And that's how continents get built, is that opening and closing of basins. The islands will collide into each other, and over time you can see the islands will become, down here at the bottom, a bigger land mass. So we can look at North America here, and you can see that this has happened numerous times. All these different names are different land masses that have collided to create the North American plate. So what I want you to look at here is up in Canada, in the northern central part of North America, that's 2.5 billion years old, the rocks there. So that area is the center, the beginnings of North America. When we come down to Texas, as you can see, it was actually built in stages. So the oldest part of Texas is just that tip of the panhandle, and it's about 1.6 billion years old. It's pretty old. Then you get into orange part here, which is still only kind of the northern half of Texas, and it's a little bit younger, 1 billion years or so. And then we get into the yellow, and the yellow there is actually everything that happened after Pangaea. So Pangaea was our last supercontinent. I think most people have probably heard of Pangaea. And then after Pangaea, the first place it started to split was the Gulf of Mexico. And we think of the Gulf as having started where it is now, but it didn't. It actually started up here, closer to Collin County. And as it has grown and stretched, it's created that whole part of Texas, the southern part. So we're going to look at this for just a second. This is the history of our supercontinents. So it started with one called and then these other supercontinent cycles. And every time that there's a cycle like that, it would make North America a little bit bigger. So you can see the size of the land masses during those early supercontinents. They weren't that big. Our early supercontinents were actually pretty small. Pangaea was the biggest one that we've had so far. We can expect another one in about 300 million years or so. And it'll probably be even bigger than Pangaea because every time they come together and collide, it makes bigger land masses. So over time, they'll get larger and larger. So if we look again at this map, but now we want to focus on Texas, we can see that we got that chunk that made the panhandle from the Columbia supercontinent cycle. We got the next part that got us all the way through to North Texas with this Rodinia, which was about 1 billion years ago. And then we got the last bit of Texas during and after Pangaea, but mostly after. And I'll kind of show how that happened. Okay. So this is what Texas probably looked like about 1.6 billion years old. So if you ever wanted to look at these maps that I'm showing tonight, you can look at, if you search on Colorado Plateau Geosystems, these are some academics that have put together maps of what they probably looked like, the continental land masses. And then they superimposed the states on them so that we would have an idea of what those states looked like at that time. So if you look here, we've got North Texas, and you can see it's just that tiny little corner of Texas is all that was there in the beginning. So Texas is actually really young compared to the rest of North America. So just to look at that map again, that by really young, it's still 1.6 billion years old. So for us, it's pretty old, but for North America, Texas is really young. So over time, more and more was built. When we get to Pangaea, we see Texas up here, and we're thinking it's Texas down there in the southern part, but it's not. That's actually South America. So Pangaea came together right across the middle of Texas, basically. So North Texas and up is actually Texas landmass. And then in the bottom of this picture, it's actually South America at that time in the early Jurassic. And what happened is we saw in the picture before, right, that there was ocean there. And then if we look over here, over time, that ocean basin closed up, the continental plates collided, and they created a mountain range. And that mountain range is called the Ouachita Mountains. And they ran diagonally across Texas. And then I think there's some of the Ouachita still left in Oklahoma and Arkansas. But here in Texas, they've eroded completely flat. So if we look at the picture down at the bottom, you can see that underneath all of our surface rocks that we have now, the Ouachitas, there's a little foot, the little root of it is still left. So it's all eroded away, and it's got our current rocks on top. And that's just newer rock formations that have deposited over time from the Ouachitas eroding and from the Rocky Mountains. We have a lot of sediments here that have washed all the way down from the Rocky Mountains. Okay, so, and you can see a little bit of the older craton is here, but it's really deep. So if we look at this next set of maps from that same project, you can see around the middle of the Jurassic. So this is the time of the dinosaurs. They're really prevalent on the land now. You can see this emerging Gulf of Mexico. So when Pangaea started to split apart, it actually started here in Texas. In the Gulf of Mexico is where Pangaea began splitting, and then it moved further in a progression over to where the Atlantic is now on our east coast. But it all started here in Texas with the Gulf of Mexico. And this picture down here gives you kind of an idea of how it happened. So we had some kind of hot magma that was coming up from underneath the earth in the mantle. It starts forcing its way up and it starts splitting the continent open. And it's not really well understood why these rift zones begin, why the continent starts breaking apart, but they do during this supercontinent cycle. So at that particular time, that place, it started with the Gulf of Mexico, and over time it stretches the continent out as it pulls apart. So even though the original rupture was actually up here close to Collin County, as it goes through this process, you can see that the continent starts pulling apart and stretching. And as it stretches out, it gets closer and closer to what we now have as the Gulf. So you can see, by the late Jurassic, the Gulf is getting pretty big. By late Cretaceous, this is when the dinosaurs were dying out. You can see that the Gulf's pretty big and now it's in its normal place. But look at Texas. The coast is still up close to North Texas here. We still don't have all of that continent yet that becomes more of our coastal area, like Houston and Galveston and Corpus and all those places. That land isn't there yet. It's underwater. And that's because it was a very warm time during the Jurassic and the Cretaceous. So the sea level was really high. So you can kind of see it was shallow across Texas. The water was shallow there, but it was still completely underwater from a little south of here to all the way to the Gulf. Okay. So I put together some pictures that show that progression a little bit better, where we actually see the Texas landmass developing. So you can see this is the late Cretaceous. The Gulf is still fully there, but see how much of Texas is still underwater. And then as we keep going into these other images, you can see that slowly the water is receding, the continents are building up. Those Ouachita mountains that were created with that collision with Pangaea, it's all eroding. And as it erodes, it's filling in that lower basin and it's kind of filling in the rest of Texas. The Rocky Mountains that are, up more in the center of the continent, they're also eroding, and because of gravity and the way that water moves sediments, that stuff is all being brought down to Texas too. So between the Rocky Mountains and the Ouachita Mountains, we have all these sediments that are filling in the part of the state where okay, I'm going to go back for a couple slides. So when we look at this, you can see I said that the continent's stretching, right? It stretches out, but it's also at a slant. So it's sloping down towards the ocean basin, but the continent is stretched. So when these other mountains are eroding away, all those sediments are filling in the low. So they're coming down past Collin County area into southern Texas and filling in that basin to build up the continent. Does anybody have any questions so far? Does it make sense? Yeah. Okay. Okay. So I want to really focus on Collin County now. So when we start looking at, this is a map of the crust in Texas, our surface crust. And we're back to these two time zones. So if we look at the Proterozoic, the really old crust, the stuff that's a little over 1 billion years old, you can see it runs right through here. So North Texas and West Texas are the old Proterozoic crust. And then we look at this time scale over here, and something around 250 million years to 99 million years, the Paleozoic areas is here. So you can see it says Mesozoic crust, and that is, and you can see where it says it's rifting and thinning. That's where the plate, the Gulf of Mexico, was opening up and moving. So you can see that this whole area is much younger, significantly younger than the rest of Texas. So I zoomed in, and there's Collin County, and so you can see that the suture area, where the Ouachitas were made, Pangaea came together literally diagonally across Collin County. So I thought that was kind of interesting when you look at that. That we're in kind of a unique position. But what I also thought was interesting, so we look here, you see this, the fault zone, the tectonic front. And if you look at the shape of the tectonic front in the purple on the one map, if you look over here in red on this physiographic map of Texas, the red is our Blackland Prairie ecosystem, right? And it really lines up with that purple. So I'm not really sure why, but there is something about being in that fault zone, and the way that the sediments were generated gave us this lovely soil that we have. Because as you probably all know, our soil is one of the richest in the world. I think the only place that's even comparable is an area in Australia. So we have great soils here, and that ecosystem lines up exactly with that fault zone, with that tectonic front. So I thought that was really interesting. It's something that I want to learn more about, how those two are related. But you can see here that tectonic front, again, straight across, or diagonally across Collin County. So it's a pretty unique area. Okay, so if we look at the geology of North Texas, when we look at our rocks at the surface here, they're all Cretaceous age, but they're a little bit different on either side of that zone. So I'm going to zoom in. The oldest rocks, of course, are up in the Panhandle, with the exception of the Llano Uplift there. That one's really old, but the rest of them, it typically goes from oldest to the Panhandle, youngest towards the coast, and those aren't even actually all rock yet. When we get closer to the coast, it's loose sediments. It's so young that it hasn't turned into rock. I used to live in Houston, and all of the homes there have all kinds of foundation problems, and there's so much movement, and it's because it's not rock yet. There's no basement rock, so those homes are really on very loose sediments that move around a lot, get compacted. It's a little safer to have a house up here. Okay, so when you zoom into Collin County, you can see there's a pretty strong divide between the rock types. So on the left side, the western side of Collin County, we have the Austin Chalk, the Eagleford, the Woodbine formations. And then on the east side of Collin County, we have the Navarro and the Taylor groups. So they're a little bit different. And it really just has to do with, that's right where that fault zone was, where Pangaea started to open. So this slide's a little bit busy, but I kind of want to show you what happens when we get our rocks. So we have sediments, and it just so happens that in Collin County, during the Mesozoic era, because the sea levels were high, we had a seaway through here. There was a very shallow ocean, that covered all of Texas, and we'll see some maps of that in just a second. But because of that, we had sediments that were developing in the water. So we had what we call mineral precipitation. So there's ocean water and it's got critters in it, the marine organisms and other things. There's sediments that are washing in, and they would precipitate out of the water and settle to the bottom and start to create these lime sediments with the accumulations from the different organisms that we're breaking down and the lime. So a lot of our rock around here is limestone, and this is why it's going through this dissolution to precipitation kind of process. It gets settled down on the bottom of the ocean floor, then it compacts and it kind of starts to glue itself together. The sediments will turn into a rock. So even though this is pretty busy, the part that applies to us is just through this area here. But it kind of helps understand how we get the rocks the way that they form. So it's all sedimentary rocks here at the surface. Okay, so this is a geologic cross-section of Collin County that shows the rocks at the surface. So you can see that our rocks here are tilted, the beds are at an angle, and that's, again, that's stretching from the continent and the ocean basin kind of pulling apart as the Gulf of Mexico opened. So we have these tilted beds. And for our area, you can see we have that the ozone formation. Then we have our Austin chalk, which we're going to see some pictures of in just a second. And then the Eagleford Formation, which is one that's really easy to find rocks from around here. And this is what it looks like at the surface. So the thing I wanted to look at here with these, we've got the oldest rocks on the western side of Collin County, which makes sense. We have younger rocks on the eastern side, but the very youngest rocks are now along our waterways. So once we have a stable craton, once the plate tectonics are done, the thing that starts to kind of shape the surface of our area, the geology, is running water. So you can see along the branches, the forks of the Trinity and into Lavon, these dark brown that have the QT on them. QT means quaternary, which is now. So we have our sediments now. The young things are all coming along our waterways. Okay. So when we look at the order of the rocks in our area with the Austin chalk, the Eagleford, and the Woodbine, the Austin chalk tends to be on top with the Eagleford underneath and the Woodbine. So we have limestone, then we have shale, and then we have sandstone. In geology, that tells us that the rocks that are at our surface right now that are visible were deposited during a time when sea level was rising here in Texas, which makes sense when I show you the next slides with those maps of the Western Interior Seaway. So sea level was rising during the Mesozoic, and that's how we got our rocks. So if we look at this map here, if we look at around 92 million years ago, you can see that most of Texas was underwater, and this seaway connected the Gulf of Mexico all the way up to the Arctic. So it's a huge seaway. You can see it covered most of the central US. Around 92 million years ago, it was pretty shallow near shore. So the sediments that we're filling in then were sand from the eroding mountains, like the Ouachitas that are now underwater, the Rockies that are now underwater. So all of that sand is coming down and depositing in this area. As we move a little bit closer to us in time, 87 million years ago, now we've got a shallow marine environment. So we have less of those bigger, coarser grained rocks with the sands coming down. Now we have more shale and clay that was being deposited. So that's the Eagleford formation. It has a little bit of limestone. It has some fossils caught up in it, but mostly it's shale. And then we move forward again, and now we're at 83 million years ago. So you can see that that western interior seaway is still there, but it's the water starting to recede. You can start to see a little bit more of the landmass on more towards the west. But here in North Texas, you can kind of tell by the different color of the water there that it was more of a deep marine environment. So this is where we start to get a lot of fossils, marine fossils, and microscopic critters that were living in the water in these deep marine environments. And as they die, they settle to the ocean floor and their exoskeletons start to form rock. Once you have, billions of them deposited. So that's how we get our Austin chalk. It's actually made out of billions of these little critters called coccolithophores. And that was just as the water was getting deeper and deeper. Eventually, we have our ice age, and the ice starts getting taken up all in our ice caps at the poles, and then the water recedes, and we'll have land again, and the western interior seaway goes away. So this slide here just gives a little bit of information on how we get those limestones and those chalks, since those are our most prolific rocks in this area. So with the limestone formation, the calcium carbonate from marine organisms, whether it's algae or corals or shells, this stuff will all kind of, as critters pass away, this stuff will precipitate out of the water and into the bottom of the sea floor. So it usually happens in very shallow areas, like numbers 1 and 3 over here would be closer to what it was like in North Texas at that time, the shallow sea. So they basically would settle to the sea floor, and over thousands to millions of years, that rock will solidify and turn into limestone. Chalk is a little bit different. It's a lot more marine organisms involved with the chalk. It's almost completely those coccolithophores. So it has to be a deeper marine environment. So you can see now where they formed in Texas before during that western interior seaway, now they are forming in the Gulf of Mexico, the chalks. Okay, so our surface rocks here in Texas look like this. So as you can see, Dallas and North Texas is all those sedimentary rocks, which makes sense because we've got all the limestone and the chalk from that western interior seaway. It's a little different, more a little west of us, because there's metamorphic rocks there from all the plate tectonics. Our older rocks tend to have metamorphized. So they're a little different, but still a lot of sediments in there too. Okay, so then once we have a mature craton, so by a mature craton, we mean that it's a stable part of the continent. So Canada was stable first, then through the central Texas stabilized, and now we're down, or I'm sorry, through the central US stabilized, and now we're down into Texas, and it's stabilizing. The mountains have eroded flat. So now what force is going to shape the land? And that's water. Once the land is flat, then the major driving force, the thing that's carrying all those sediments around, is land that's eroding at the top of mountains that goes into the rivers, and rivers carry those sediments down to other places and deposit them downstream. So some of the places around us where we can see these formations usually is where there's water. So if we look at This is a picture, some pictures from Beavers Bend Park. And that's the Eagleford Shale there that you see. But we need water because the water cuts down into the sediments, past the sediments, so that we can actually see the rock formations underneath all of our soil. So you can see that here. Rick Travis was kind enough to actually climb down that gully for me and take some rock samples, which was kind of nice because it was muddy. And then another place where you could see it, a place we volunteer, is the Heritage Farmstead. And as you can see around the waterway there, the water's cut down through the sediments enough that we can see the shale there at the surface. Oak Point Park, I wasn't able to get close enough to ID the rock. I think it's another shale, just looking at how soft it is. But Oak Point Park and the waterway there, you can see some nice rock formation. You can also see the power of erosion. So if you look at these trees, they're barely hanging in there. They you can see the roots are bare. Some of these guys are already getting ready to fall into the water. So you can really see the power of water and how it can erode those sediments that they then carry downstream. And that's how these areas build up. Okay, so this is a Connemara meadow. My friend Brenda Clark was nice enough to give me some pictures she's taken of the water around there. So you can really see those eroded roots. It's harder to see rock around Connemara, but you can see how important water is in that area. Okay. And then this top picture up here, I'm also a geology professor, and I took some of my students out to the herd, and we looked at that limestone outcrop. So if you look, where we have our meetings at, the SRC is sitting on this big limestone outcrop. And you can see, like below my students here, where the water running down is actually carving out paths through the limestone. You can see that it's eroding pretty fast. It's an interesting place for them to have chosen to build that building because there's a lot you can see just underneath that deck. There's a lot of erosion. Don't worry, it's safe. They've got concrete pillars underneath there that it's a sturdy building. And then I took a picture of it because this is kind of a special limestone. It's called oolitic. So it gets these interesting little other rock pieces kind of caught up in the limestone while it was forming. And they're called oolites. I thought it was kind of cool. Okay, so that was all North Texas. Now I'm going to take you, what time is it? Now I'm going to take you on a little visual tour of Texas from the beginning to now, where it was located, because Texas wasn't always where it is right now as far as latitude and longitude are concerned. So about 750 million years ago, this is really early on. So we're talking, you know, our first supercontinent or two. So there's really only the panhandle. This red dot here is the approximate location of Texas. And what I want you to see, this white line across there is the equator. The white spot down there is the South Pole. So a long time ago, Texas was actually south of the equator. The Llano uplift is probably the only rocks we have at the surface from that time period. I don't know if you guys know where that is, but it's right smack in the middle of Texas is the Llano uplift. And you can get some beautiful rocks from there that are unique to Texas. So this was during an ice age, so you don't see a lot of landmass yet because we're early on in the continent cycle, supercontinent cycle. Red and green algae are starting to proliferate. So we don't have much atmosphere yet at this point, 750 million years ago. We don't have much oxygen, but we've got the algae that's starting to photosynthesize. 600 million years ago, now I want you to look. So Texas is really far south now. You see the South Pole way down there. the equator is way up there. So, whoops. So Texas has traveled south um, as these continents are coming together. Multicellular life is starting to evolve. This is the Pangaea supercontinent that happened right at the end of the Proterozoic. So this is before life really exploded. We're still just small critters, microscopic. Now they've gone from single-celled organisms to multicellular life starting to evolve. But I just wanted you to see, this is still just the panhandle. I wanted you to see how far south Texas was, not close to the South Pole. Okay. So 550 million years ago, now that the Texas outline's starting to show up, after Pangaea splits off, Texas is bigger now. It stole some continent from this other piece of land. As they're starting to split apart, you see that ocean basin forming, but look at the tilt. North America is completely sideways from the way it is now. So it's tilted over. We're still way south of the equator, closer to the South Pole. Now Texas is starting to get sedimentary rocks. They're being deposited along the coast, but look at where the coast is. We're not talking about our current coast. We're talking about the coast as in it was North Texas at that time. But life is starting to explode. The Cambrian is just getting started. Life is in the oceans only still, but we're getting lots of shelled organisms. Things are starting to develop exoskeletons. We're not quite to fish yet, but life is really starting to proliferate and change. We're starting to diversify. 500 million years ago, Texas is still on its side. Look at those water levels. The whole continent almost, the part of it that is the United States, is completely underwater. We're getting closer to the equator now. We're starting to get a lot of limestones. As you can see, it's still a shallow sea, so we get a lot of limestone being deposited, and the fish are starting to show up in the oceans. So now we get fish, but they don't have jaws yet. They're starting to develop backbones. So life is very much changing. 470 million years ago, North America is now starting to rotate. So we've rotated a little bit from before. We're not completely sideways. I think though that it's moved a little bit further away. No, it's still pretty close to the equator. Coral reefs are starting to emerge. So now coral life has started to develop, but we still don't have any complex life on land. All right, 450 million years ago, the area is still completely underwater. We're creeping a little closer to the equator. Texas is really starting to rotate some more, or that whole continent. Life in the seas now is very diverse. On land, algae is the only multicellular plant. So plants aren't developing as fast as life has developed. 430 million years ago, still underwater. So sea levels are still really high. Sediments are starting to form around the Llano Basin. We're getting a lot of limestone, and limestone is what forms caves. So we have a lot of limestone that's being deposited in Texas because we're still in that shallow sea. Plants are starting to evolve vasculature, and this is huge. Before, plants were kind of like lily pads. They could just kind of float along the surface. They didn't have anything sturdy enough in their stems to hold them upright. So as they evolve vascular, they can start to stand upright, and that's huge for trying to get onto land because they need to be able to hold themselves up. So plants are finally starting to evolve. Marine life is getting bigger and more complex, larger fish. Okay, so now 400 million years ago, we're right in the middle of the Paleozoic. But look at how far south we've jumped. Now we're back far away from the equator, which is way up at the top here. We're getting closer to the South Pole again, but North America is rotating more, so it's starting to get there. It's still pretty shallow here. This is another supercontinent coming together. This is pretty shallow here, which means more limestone. So you can see why we have so much limestone in Texas. Insects are now on land and they're starting to diversify. Fish are starting to develop fins. And now we're starting to see some vertebrates on land. So we're starting to get our closer to amphibians. So we keep moving forward, 370 million years. You can see Texas is rotating. We're getting closer to the equator now. More land mass is visible. So it's not so, the sea levels aren't quite as high. Marine life is still diversifying. The plants are starting to get more and more complex. Not really around Texas though, because we're underwater. Okay, 340 million years ago, we're moving up. We're in the Carboniferous now, which is when the oxygen really starts to proliferate. Our plants are really starting to diversify. They're spreading out. So we're getting more and more oxygen into the atmosphere. We still have a lot of limestone that's being deposited in Texas because it's in a shallow area, but it's also eroding very heavily. But there's a mass extinction in our oceans. So because oxygen is increasing, our anaerobic life is dying off. So we have an extinction in the oceans. But reptiles are really starting to evolve. So you win some, you lose some, I guess. Okay, so now we're moving forward. 300 million years ago, there's some tectonic uplift happening in Texas. So this is Pangaea is starting to come together. An ocean basin is closing. You can see those Ouachita mountains there are starting to form as these continents collide. There's still limestone deposition going on because those sea levels are still kind of high. And now plants have root systems. So they're starting to be better anchored. They can handle better, more severe climates. And the trees are starting to get really tall and create canopies. And this is a time period we have so much oxygen in our atmosphere now that the giant insects are really starting to proliferate. So then we move into about 280 million years ago, Pangaea is formed. You can see the higher elevations now for those Ouachita Mountains that have been created and into the Appalachians. We have this giant reef system that is building up in the part of Texas that is still underwater. And those actually become our Guadalupe Mountains. So we have a mountain range that's actually made out of reefs. So that's pretty cool. It's not your normal granite. Then we have limestone all across the high plains because the water level is still high. Pangaea is together. Because Pangaea is together and it's this massive continent, we have very extreme climate. Whenever there's a supercontinent that's fully together, the climates in the center tend to be really, really hot and dry. So they're pretty extreme. So now we're moving forward 260 million years ago. We're headed towards the end of the Permian. And that is our biggest extinction event ever. 90 to 95% of all life on Earth was wiped out during this extinction event. So without plants, we have very little food supply. There's very little oxygen in the atmosphere because the plants have all died out. So we're losing our large reptiles, the really large insects are gone. And this all happened because of volcanism over in the Siberia area. Those volcanoes were erupting for millions of years, and it was spewing so much sulfuric gas into the atmosphere and so much ash that our upper wind system spread it across the entire globe. And without as much sun, with this global cooling period that was caused by all of the volcanism, the plants didn't have sunlight. They start dying off. The sulfur in the atmosphere starts settling into the oceans and acidifies the oceans, and the animals that evolved there, those critters couldn't survive. So everything is dying off. And it's actually called the Great Dying. But that gives rise to other things. So that was the age of the fishes. Now we're about to come into the age of the dinosaurs. So 280 million years ago, the Guadalupe River Mountains are still developing as that giant reef system. Texas is still sitting right at the equator, so it was really hot. The limestone is still developing in our area. Whoops. I went the wrong way. Sorry. Okay, so 240 million years ago, our oxygen levels are greatly reduced because of that plant extinction. But now we're into the Mesozoic. So this Triassic area is kind of the ancestors of dinosaurs. They're the little chicken-sized ones. Mammals are starting to show up, but these guys couldn't compete with the dinosaurs, so they pretty much stayed in the shrubbery. They were kind of hidden. And then birds, of course, are an offshoot of dinosaurs, so they're kind of starting to develop too. We move further into the Triassic. Now, look, North America is pretty well straight up and down. It's almost there. We've moved a little bit north of the equator. And now flying things other than insects are starting to show up. We have those big flying reptiles. More mature dinosaurs are starting to show up. They're still very simple critters. They're not T-Rex yet, but we're starting to see dinosaurs, and we had them in our area. So yeah, it's still very warm. We're in the inside of the continent, but as you can see, that seaway is gone. So now we're getting more land-based sediments here with like sandstones. Okay, 200 million years ago, we're going into the Jurassic. North America is pretty straight up. We're still moving away from the dinosaurs. You can kind of see the Gulf of Mexico trying to get started. So Pangaea is about to start splitting up. You can see the Gulf of Mexico, the very beginnings of it, starting to creep in there. 170 million years ago, the Gulf of Mexico is pretty well forming, and you can see the Atlantic Ocean basin is starting to open up. So Pangaea is really splitting apart. North America is going its way. Africa and South America are starting to split off and move away. We're moving much more further north away from the equator. Ocean life is starting to diversify again. Earth is still very warm. Birds are evolving. Dinosaurs are really starting to thrive and diversify as well. Now we're moving to the end of the Jurassic. You can see that the Gulf of Mexico is pretty big now. It's getting closer to where it is right now. We're getting further away from the equator, so it's starting to get cooler in Texas. Lizards are appearing. Placental mammals start to evolve, but dinosaurs still dominate. So the mammals are still living in the brush and the shrubs and the forests. They're still trying to hide. and large marine reptiles dominate our oceans. So the mosasaurs. Okay, we're moving more into the Cretaceous, still a lot of dinosaurs. The climate's still pretty warm, but we're getting much further away from the equator. You can see now Texas back underwater. So we're starting to, the water, sea levels are rising again because it's such a warm climate. All the ice caps are melting. We have really large reptiles, really small mammals, but now flowering of plants have evolved. And that's huge for flowers because once they have seeds that can spread, then they can move out of their ecosystem. Before they had to kind of rely on animals to move them around. But now with seeds, the wind can pick them up and carry them, and plants can now really proliferate across the land. Okay, so into the middle Cretaceous, that western interior seaway is starting to form. So poor Texas, it got out of the water, now it's back underwater again. It's moving further away from the equator. The continents are splitting farther apart. Now we're starting to get limestones. So we were getting the sandstones. Now we're into the limestones. And this is where dinosaurs with those really heavy plated skulls are starting to form. They're showing up. They're not going to be around too long, though, unfortunately. Oops. Okay. So 90 million years ago, that western interior seaway that I've already talked about is fully formed. It's linking the Arctic and the Gulf of Mexico. The whole central United States is completely underwater, more limestone. Mammals are starting to be closer to what our modern mammals look like. Birds are really developing. They've completely split from the dinosaurs that are their ancestors, and they're starting to develop their own line. And insects are emerging again. Okay, so now we're at the end of the Cretaceous. So this is another extinction event, but it's only about 70% of life on Earth this time, not 95. So it's not as bad. And the demise of the dinosaurs brings us to the rise of the mammals. So there's always good with the bad. It was another big volcanic incident that was happening with the India traps, plus that big asteroid that hit in the Gulf of Mexico, close to Mexico. Those two events together created the mass extinction. Texas is coming back out. The western interior seaway is dried up. So now it's sands and clays that are being deposited. Modern river systems are starting to form, and our dinosaurs and our flying reptiles are gone. But mammals can finally come out of the forests and the shrubs. Okay, 50 million years ago, the Rocky Mountains are eroding, and all of those sediments are pouring down into Texas. So we're getting lots of sand and clay. Birds, mammals, reptiles are all diversifying and spreading out, and they're super happy because the dinosaurs aren't there to compete with. And whales start to evolve. So some of those animals from the ocean or from the land have gone back out into the oceans, and we get our aquatic mammals. Okay. 35 million years ago, Rockies are eroding, Ouachita Mountains are gone. All those sands and clays are pouring into Texas. Primates are evolving. Earth is cooling. So sea levels are dropping, and deciduous plants are and deciduous plants are starting to proliferate. Okay. 20 million years ago, now we're getting closer and closer to our modern age. So it's looking pretty good, right? The Appalachians are still over there, but they're eroding. No Florida yet. Why? Because the Appalachians haven't eroded enough. Florida was a reef, And the Appalachians eroded enough to cover the reef, and that's where Florida came from, the erosion of the Appalachian Mountains. Over here, we've got the Basin and Range province that's growing. We've got our whole subduction zone over on the western coast that has our Cascade Mountains and volcanoes that are growing. Hominids are emerging in Africa. Mammals and birds are evolving into their very modern form. So a lot is going on with life now. Oops, going the wrong way. Okay, so that brings us to now. This is our current iteration on Earth. You can see our Basin and Range province is over here. That's where the continent is starting to try and rift again. So that supercontinent cycle is starting all over again. But now here it is. It's in the Basin and Range province where it's starting to split. So it's moved to a different location. So we have a lot of tectonic movement in that area. Then we're over here, we've got a transform fault in Baja California, and that part of the plate with the San Andreas fault. That's all trying to break off. It's going to move eventually, but we're talking millions and millions of years from now. We won't be around to see it. Everything's pretty quiet over on the eastern front. That's our passive margin. You can see here where the continent is very stable and flat, and most of Texas is in that stable craton where it's flat. It's already had all of its exciting tectonic activity, and now it's water that's taking over. So river valleys start down cutting. The Trinity River has been around for 5 or 6 million years now. So all the sedimentation that's happening in this part of Texas is along riverways and coastal zones. But the Rio Grande is part of that Basin and Range province. So when the continent does split apart, if it splits apart, it's still going to involve Texas because now it's going to be on the west side of Texas at the Rio Grande. Okay, that's all I have for you guys. Is there anything you have questions about? Any slides you want me to go back to? It's been really quiet.
Well, I did have one question, and I don't know if this shows that I don't know what I'm talking about, but I'm trying to learn. But at the very beginning, you had one or two slides, and it was it the Llano Basin that caused the Llano uplift? Is that all the same kind of talk?
Well, I don't know a lot about the Llano uplift. I don't know much about that area. I just know that it's our oldest rocks. They're up there with the I think it's about 1.2 billion years old, so it would be probably that second supercontinent cycle. But I think that the basin is just the area around it that's eroded more, is my understanding. The Llano uplift itself is, as it says there, it's gneiss and schist. Those are metamorphic rocks that are really, really resistant to erosion. So those guys stick around. They're really hard rocks. They don't want to break apart. And I'm wondering if the basin is just the stuff that's already eroded away. That's what I think. Does
Oh,
that
thank
answer
you.
your question?
Yeah, thank you.
Okay. Is there any other questions? Nope. Okay. I guess we're done for the night then.